Let's go back to the idea of the expansion of the universe. Okay, so when we talked about it before, we talked about how everything is expanding. Now, this rate of expansion, how fast the universe itself is growing, is probably not always going to be at the same speed. Okay, so as an example, one of the forces that we know that works on a universal scale is gravity. And gravity is always attractive. Gravity is always pulling things together. What this would mean is that as the universe is expanding, gravity should be pulling on it, which should slow down that expansion rate. Okay, so that means that the expansion should be slower today than it was in the past. So we kind of get this idea that how the universe is expanding should be changing in time. Well, we can actually go and do things to figure out how this has happened. Specifically, there have been several studies done looking at the apparent magnitude of type 1a supernovae and comparing that to the redshift of the galaxy that we see it in. So on this graph, up and down, we have the apparent magnitude of the supernova, which we can use to determine distance. So up and down, we're looking at the distance. And then along the bottom, we're looking at the redshift to the galaxy that the supernova happened in. Okay, now the redshift, z, is going to be related to the expansion of space, the expansion rate of the universe. So we have expansion of the universe compared to distance, and remember, distance is also related to time. Okay, so we can compare distances and expansion rate, or time and expansion rate. Well, all of these studies have concluded that the expansion rate is actually increasing. The expansion rate is faster today than it used to be in the past. Now, this is not at all what we were expecting. This first paper that pointed this out was published in 1998. So this is somewhat of a relatively new discovery. It's over 20 years old. But it is still kind of recent as far as our developments and understanding in the realms of physics and astronomy. Now, our best guess as to what could be causing the expansion rate to go faster and faster. Remember, we had assumed that it would be slowing down. In this case, we see it's actually going faster and faster. This is what dark energy actually does. Dark energy leads to a faster and faster expansion rate. So this graph is another one of these. It's a little bit hard to interpret. What you need to understand is each of these different colored regions are different regions of possibility, of probability, based on different measurements. So in this, we're looking at the amount of dark energy compared to the amount of matter. Now this includes both normal matter and dark matter. Okay, so how much dark energy is there versus how much matter is there in the universe? So this blue region is the amount of dark matter to dark energy that is possible based off of supernova data. So what we just saw in the previous information. The green region is what is possible based off of what we've learned from the cosmic microwave background. So this is what's possible from the cosmic microwave background. And then this kind of weird brown line is what is possible based off of cluster data. So how is it that galaxy clusters have positioned themselves and the size of voids and all that stuff? Well, we get from the large-scale structure. Well, the only place that all three of these different measurements agree is right here at this red dot. That red dot tells us that the universe is made of 68% dark energy, 27% dark matter, and only about 5% what we call normal matter. This is the stuff that makes up us and the Earth and things like the sun. Okay, this is the normal matter. Now, what this means is we don't know what 95% of the universe is actually made of. We only understand 5%. Now that seems terrible, but it's actually awesome, because it means that astronomers still have jobs, because there's still 95% of the universe that we have to figure out. Now, from all of this, we see that the universe is dark energy dominated, and we understand that dark energy is leading to a faster and faster expansion rate. With this understanding, we can now talk about the eventual fate of the universe. So as the universe stands right now, we still have galaxies, and there's still star formation within galaxies. And we're still in a stage that we can see light all the way out to the edge of the observable universe. However, because the expansion rate is increasing, This means that distant galaxies are going to become more and more redshifted faster and faster. So their light will become so redshifted that at some point in the future, we will only be able to see galaxies within our local cluster of galaxies. All other galaxy clusters will be lost from view. As this is happening within galaxies, eventually star formation is going to end. The galaxies are going to use up all of the interstellar medium. Then stars are going to die out. First, the high-mass hot stars die out, then the medium-mass stars, and then finally low-mass stars, until eventually even stars have all died out. What this means is the eventual fate of the universe is going to be perfectly black, perfectly cold, and completely depressing. I don't like to think about this. So, let's jump on to another topic real quick. Because we understand the expansion history of the universe, we can actually go back in time and determine when did the universe begin. Okay? So the idea is that the galaxy is expanding now, so if we go back in time, everything had to be closer and closer together. Well, based on the amount of dark matter, dark energy, and all of this stuff, the universe is about 13.8 billion years old. Okay, this is a number I recommend you know. The universe is about 13.8 billion years old. And next lecture, we're going to talk about the beginning of the universe.